Good morning. First of all, I would like to thank the organizers, especially Josie and Sillard, for inviting me down here. And it is my great pleasure, especially for this particular conference, because Dr. Lester Packer and Ann Packer are here. I very rarely get an opportunity to see them. And so this is a very special conference for me. It is also very special because a lot of the associates of Dr. Packer are also here. And as some of you know, that I graduated from that lab several years ago. And probably I will not be standing over here and talking to all of you if I was not associated with Dr. Packer, because he gave me a very special opportunity to work with him way back. So having said that, today, as you can see, the title of my talk is about curcumin, and I'm specifically asked to talk about the role of curcumin in epigenetic changes. So normally, I do not talk about it. Usually, the kind of conferences I go to is primarily cancer. As all of you know that I'm from MD Anderson Cancer Center. So the cancer conferences is my major focus. And even within cancer, it is inflammation. So we are very much of the opinion that inflammation plays a very important role in various chronic diseases, including cancer. And if you can control inflammation, you can control a lot of these chronic diseases. So that's what primarily I talk about. So I just first would like to address this topic very briefly initially before I go on to epigenetic changes, even though those epigenetic changes are also linked with the inflammation. I think we are here to talk about pro-oxidant, to talk about antioxidants, to talk about inflammation and all of that. And it is generally believed that inflammation is bad or pro-oxidants is bad. And the fact of the matter is they are not bad at all. You need the pro-oxidants to kill the tumor cell. You also need the pro-oxidants to form the tumors. It is invariably what it turns out that, as you can see, that here is a fire. The word inflammation comes from inflame, fire. So when the fires are well under control, as you can see, you have a kitchen, you have a living room, you have a bedroom, all the fires are under control and everything is fine. So you need inflammation. Without inflammation, the life will become very difficult. However, it's same inflammation when it gets out of control, as you can see that what kind of havoc it can cause. So it is this kind of inflammation or is this kind of pro-oxidants that what we need to control, not this one. And if we try to control this one, then there won't be any more life. So having said that, so I think that the question is, where is this inflammation is coming from? And as you can see from the cover of this immunity, it is all about cytokines. And I happen to start at a time when the word did not exist. And so it was not clear at all that at a molecular level what causes inflammation. And as of today, we have this the word cytokine, which is basically a molecule that are produced by the cells and cause fire. And we happen to discover one of those molecules, and that is called tumor necrosis factor. And that turned out to be one of the primary mediator of inflammation. And again, we realized that TNF is a double-edged sword. That, as you can see, that TNF is a very important part of the immune system. If it remains in the immune system, it is therapeutic. However, once it gets out of the immune system, it can cause all kind of problems. So here it has become a superfamily, that there are 18 members of the TNF superfamily now have been found. And and here I say 25 years later, mind you, we discovered this in the early 80s. And 25 years later, I call a golden journey. And this golden journey word has a double meaning. And one of the meaning is curcumin, turmeric, which is yellow in color, and that controls TNF. So, and we also have a monograph in case if anybody is interested, inflammation, lifestyle, and chronic diseases and silent link, that how important it is playing a role. And so question is, what is the source of all this inflammation? And as you can see from here, that here you have a smoking, here you have a radiation, you have alcohol, you have a diet, obesity. These are all very, very, very pro-inflammatory situations. So in addition, you have all kind of environmental pollutants. You have a grilled food, fried food, red meat, virtually all kind of bacteria that have been linked with cancer, all kind of viruses that have been linked with cancer without exception. They activate inflammation. And cigarette smoke, here is a stress, psychological stress, mechanical stress, physical stress, chemical stress, any kind of stress will lead to inflammation. And so is ultraviolet radiation, alcoholic beverages, and so forth is all leading to inflammation. So this is our working hypothesis over the years, and that is that dysregulated chronic inflammation caused by lifestyle factor mediate chronic diseases, including cancer. So therefore, we must find the ways to control this. So here, for example, you have a tobacco smoke that lead to bronchitis, which means inflammation of the bronchus, and that lead to lung cancer. Here you have a Helicobacter pylori lead to gastritis, which is gastric cancer, and that lead to gastric cancer. And similarly, cervicitis, inflammation of the cervix, lead to cervical cancer. So invariably, it is this pro-inflammatory condition that is leading to cancer. So again, question is at molecular level, how do we define inflammation? And it turns out that NF-kappa B is a major mediator of most chronic diseases, including cancer. And if you were to inhibit, you can prevent and delay the onset of this. So here you can see that there are over 500 different genes as of today that have been identified that are regulated by NF-kappa B, and it is all listed over here, and this list is constantly becoming longer. So here you have, as I mentioned, that we happen to discover TNF, and so far nobody to my knowledge has found an agent which is more potent than TNF as an activator of NF-kappa B. In a picomolar amounts, it can activate NF-kappa B, and it can do so within a matter of a minute or two. So here it will activate NF-kappa B, lead to IL-6 and STAT3, and this NF-kappa B has been linked with the survival of the tumor. It has been linked with chemoresistance, radioresistance. It has been linked with the proliferation of the tumor, bone loss, invasion and metastasis, and angiogenesis. And we can block all of that by suppressing NF-kappa B. So here even chemotherapy and radiation, which is normally used for treatment, they are both activator of NF-kappa B. So if cancer is by itself alone is not making you worse, that the chemotherapy and radiation will further make you feel worse, as some of the people who have a cancer know that. And there are some inhibitors of NF-kappa B, which are some of the either antibodies or the kinase inhibitors that have been identified, and some of them work through the suppression of NF-kappa B. So here you can see this NF-kappa B is required for the transformation. It is required for the survival, proliferation, invasion, angiogenesis, and metastasis. And it takes 10 to 20 years to go from here to here, and 10 years to go from here to here. There's total 30 years of inflammation, mind you. It is not just overnight. So most of it believe the cancer starts at the age of 20, and they are manifested at the age of 50. So you can very well imagine that it is a very, very long term, and it is a matter of lifestyle. So this NF-kappa B is not just linked with cancer alone, that as I mentioned, that both TNF and NF-kappa B is a very important part of the immune system. And without NF-kappa B, we don't have immune system. However, when it gets dysregulated, Here you can see all the various chronic diseases that NF-kappa B has been linked. And something like aging. Aging is not a disease, but as we get older, NF-kappa B comes up and a lot of these chronic diseases take over. So I'm going to show you some evidence that even curcumin, which is known to block NF-kappa B, even that can prolong the aging process. So NF-kappa B is, I think, bottom line is the enemy within, and it can be a friend if it remains in the immune system, but it becomes a foe moment it gets out of the immune system. So NF-kappa B in cancer is especially a matter of life and death. So question is, what we really need is a fire extinguisher that can control NF-kappa B, but the most important thing is safely. There's no problem, when it comes to drug development, pharmaceutical industry can easily come up with NF-kappa B inhibitors, and they have, but none of them are very safe. And I'm going to show you that some of the better ways to control NF-kappa B. So, and these are some of the agents that have been identified from our group. That here you can see that we have identified different kind of spices, and we have identified the active compounds. And here is Ayurvedic medicine, here are fruits and vegetables, here is traditional Chinese medicine, and here are various other kind of plants. And they are all NF-kappa B inhibitors. And not only that, we have identified the active compounds from all of them. And these are the active compounds. We know exactly where they bind in the NF-kappa B pathway and how they inhibit. And today I'm going to share with you that some of this regulation of NF-kappa B is through the epigenetic changes. And I'm specifically today going to focus on curcumin. However, I will mention some of the other agents that control NF-kappa B as well. So curcumin, for some of you don't know, it is a compound that comes from a plant called Curcuma longa, and that's what this plant looks like. And apparently in French, it is called either curcuma or surfan des Indes or terra maritis. And one of the most common name is turmeric, and that's probably where the word turmeric came from. So, and this is the active compound, and this is what gives the yellow color. Actually, this is a rhizome that is, when dried, gives rise to turmeric, and this is the 2 to 5% of this compound is present in turmeric. So, and we were the first one to show that curcumin is the most potent inhibitor of NF-kappa B, and as you can see that TNF is activating NF-kappa B, and with increasing concentration of curcumin, you can completely suppress that NF-kappa B. And as a result of which, that most of the cancer-causing genes, that whether they are tumor cell survival genes, or they are proliferation genes, or they are angiogenesis and metastasis gene, without exception, they are all down modulated by curcumin, as you can see over here. And they are all regulated by NF-kappa B. So, and those are not the only pathways that by which curcumin is working. It is a multi-targeted. And as of today, as you can see, there are transcription factor, inflammatory cytokines, enzymes, kinases, growth factor, receptor. They are all modulated by curcumin. So, it is multi-targeted. So, and the amazing thing is, how does curcumin do whatever it does? And it turned out these are some of the proteins curcumin actually physically binds to. And most of the proteins that are involved in epigenetic changes, I'm going to show you that curcumin actually physically binds to and inhibits the activity. And so these are some of the additional proteins, and the binding could be anywhere from picomolar amounts in terms of the affinity to millimolar amounts depending upon the protein. And which molecules of curcumin are responsible for the binding, that is also very much delineated. So today the primary focus is epigenetic changes. So whenever we talk about epigenetic changes, we mainly talk about three types of changes. Either there is a histone modification, which could be mediated through histone acetyltransferases or histone deacetyltransferases. Or there could be a DNA methylation, and which is primarily mediated through DNMT. or the microRNA changes, which is a gene expression. So, and here are some of the various areas that these various enzymes bind to and causes the changes. And there is, when it comes to histone transferases, that there is a communication between histone acetyltransferase and histone deacetyltransferase. And here are the various pathways and various genes that have been shown to be modulated by this pathway. And NF-kappa B in particular appears to be controlled by protein acetylation and even protein P65 methylation. So both of them play a very important role. And here, as probably if you put the word NF-kappa B in the PubMed, there will be now more than 100,000 publications. And mind you, more than 50%, and I will not hesitate to say more than 80–90% of the publications are looking at NF-kappa B activation by TNF. However, this NF-kappa B is activated by a wide variety of other agents, and the pathway there are very different than that of TNF. And we understand the best that how TNF activates the NF-kappa B. So having said that, what we found that TNF activates HAT, that leads to P65 acetylation, and that leads to NF-kappa B activation. And I'm going to show you some nutraceutical, and that the way they seems to be inhibiting NF-kappa B is by inhibiting HAT. So here, for example, that you can see that there is a compound called evodimine, and it comes from a plant called Evodia, which is used as a part of the traditional medicine. And we showed that it does inhibit NF-kappa B and through the inhibition of IkK, and it inhibits the P65 phosphorylation, acetylation. And here you can see that in response to TNF, P65 undergoing acetylation, and if you add evodimine, you completely inhibit that. Here is another one called indole-3-carbinol. And this indole-3-carbinol comes from all these various plants. And again, we showed that indole-3-carbinol, here is a TNF inducing acetylation of P65, and indole-3-carbinol completely inhibits it. Therefore, there is an inhibition of NF-kappa B, and that leads to the downregulation of all the genes that are linked with the cancer metastasis and proliferation. So similarly, here you can see that here is anacardic acid, and this anacardic acid comes from this cashews. And again, this one can TNF can induce acetylation, and here is anacardic acid can inhibit. If you look at the acetylation of whole bunch of protein, it is induced here by TNF, and by adding anacardic acid, you can completely inhibit. And here you can see the NF-kappa B activation, and that is inhibited by anacardic acid. However, if you knock out a HAT by S300 by using siRNA, now you can see anacardic acid has no effect at all on the NF-kappa B, indicating that HAT is the primary mediator over here. So here is another one that you can see, which is coming from the traditional Chinese medicine called triptolide. It is called God of Thunder's wine. And apparently you can see that it is acetylation, and triptolide can inhibit it. Here again you can see acetylation, and triptolide is inhibiting that acetylation. And again it is doing that through the inhibition of HAT. And here is a curcumin. Again you can see the acetylation, and here inhibition of that acetylation by curcumin, that when you add with TNF for P65. So apparently it has been very conclusively shown that curcumin directly binds to HAT, and it will inhibit HAT quite effectively. And and here you can see that inhibition is through the ROS mechanism, that it is quenching ROS, therefore it is blocking HAT. And here they actually showed the binding of curcumin-2 hat. And here it is interesting that you have a curcumin and then you have a tetrahydrocurcumin, which is this double bond is missing. This curcumin will inhibit NF-kappa B. This is a white curcumin that will not inhibit NF-kappa B. And therefore, it was found that this white curcumin, which is a tetrahydrocurcumin, that has no effect on hat at all. So you need those two double bonds for curcumin to bind to hat. So here is some other reports about that if you inhibit hat, that leads to caspase activation, and there are also reports about curcumin that it will activate HDAC2, and that will also lead to the inhibition of hat. So I think, and there is also evidence in vivo that that curcumin is quite effective in vivo in inhibiting hat. And apparently there is a hypertrophy of the heart that is abolished by curcumin. 2 weeks of curcumin is enough to inhibit the hypertrophy, and that is a hat mediated. So my time is running short here, and here is another model where it has been shown that curcumin is working through the inhibition of hat. And here is another septic shock model that has been shown by others, that curcumin will work not only in vitro but also in vivo through the inhibition of hat. There is also HDAC. Curcumin will also block the HDACs, and that valproic acid and SAHA are the two compounds that have been approved by the FDA as HDAC inhibitors. And we have shown that this SAHA is a very good inhibitor of NF-kappa B, and we showed the mechanism that how it works. And then if curcumin and both acts as a both inhibitor of hat as well as HDAC, as has been shown by others. And here you can see there are various other reports about the inhibition of HDAC, and this is valine that gives rise to valproic acid, and coming from this plant called valerian, and that is the best known HDAC inhibitor. This is a DNMT, and again this is a curcumin is an inhibitor of that also, and apparently it physically binds to DNMT. And so here you can see some more reports that have been published by others, and it goes on, and there is also in vivo. And I know my time is running out, and I just want to quickly mention about the microRNA. There are a number of microRNA that curcumin is modulating, and here NF-kappa B has been very closely linked to various microRNA, as you can see from here, and here are some more. And these are all the microRNAs that you can see that has been linked to NF-kappa B and STAT3 pathway. And here are the various chronic diseases, pro-inflammatory diseases that have been linked with this various microRNA. And here is the curcumin that it will upregulate all these microRNA and down-modulate these. So there are a number of reports that have been published, and this is a cigarette smoke again that we were the first one to show that it activates NF-kappa B, and cigarette smoke-induced NF-kappa B activation is persistent, and curcumin will block that NF-kappa B, and more recently we showed that it does so through the induction of various microRNAs. Several microRNAs are upregulated while others are downregulated, and here you can see, for example, cigarette smoke will upregulate this microRNA and curcumin will downmodulate, and so is over here. So I think here are some additional that microRNA that you can see that which are modulated by curcumin, and these are various proteins. And having said that, since this is an aging conference, as I mentioned, that there is a lot of data out there on curcumin prolonging the aging. So here is all kind of Drosophila, and then there are also reports in mice, and here is a paper that just came out in Nature that with C. elegans, again, that they found that amyloid binding proteins molecule, which is curcumin, is one of them that will also induce the prolonging of the lifespan. And there are some clinical trials that have been done with 80 milligram curcumin per day. You can see here is a 40 to 60-year-old people, and they gave a curcumin, N is equal to 19 over here, placebo is equal to 19 for 4 weeks, and they could see here a whole bunch of changes with it that are occurring. And so I think that we have a review. I know I went through very, very quickly. If anybody is interested, can look it up. And there is a whole talk about epigenetic diet, and that's what we are talking about. And I stop right here. Thank you for your attention.
Of curcumin, is it mostly sulfonated, glucuronidated, or methylated?
I'm sorry, I didn't get your question.
Oh, on the liver metabolization
Yes.
of curcumin, is the primary pathway sulfonation, glucuronidation, or methylation?
Yes, that is occurring on the curcumin itself. And that's what will inactivate. If there is a glucuronidation of curcumin, it is no longer active.
So it's sulfation?
So is sulfation. So mainly, primarily, if you give a curcumin IV, it undergoes reduction and forms a tetrahydrocurcumin like what I showed you. On the other hand, if you give orally, it undergoes sulfation and glucuronidation, and both of those curcumin molecules are inactive.
Hi, I'm John
Yes.
Berber. I have a practical question. I often cook with turmeric and olive oil, and I wonder if I'm getting an adequate intake of curcumin that way, or if there's some special benefit to taking the extract itself.
Well, I think traditionally speaking, you are doing the right thing, and that's what normally people do. And the question is there adequate amount of curcumin that you are taking? And that is a very, very difficult question. And why? Because we don't have any kind of biomarkers, that we are trying to determine. But I think that is something that we are actually setting up right now. And so I think that, but under those conditions that what you are taking, curcumin is still fully active.
Bharat, congratulations for a great talk. I have a question based on an unexpected and paradoxical result finding, because in knockout mice of NADPH4, there is an increase in tumor development in the liver. So in the long term, perhaps the effect of some pro-oxidant mechanisms may be beneficial to prevent tumor development.
Yes.
What's your opinion in this regard?
See, as you know, that virtually most of the reactions in the body is one electron transfer reactions, which means there is naturally a production of pro-oxidants. And in a lot of cases, that pro-oxidants are required to keep things under control. It is only when there is too much production of the pro-oxidants, that's what we want to control. And I think that it is a balance between the antioxidant versus pro-oxidant. I showed you the data here on the suppression of NF-kappa B by curcumin. And it turned out that this suppression of NF-kappa B by curcumin is primarily through the pro-oxidant mechanism, not through the antioxidant mechanism. So you need the pro-oxidant even to get the anti-inflammatory effects. So I think it depends upon the type of situation that what we are talking about.
I want to know if we were to take curcumin on long term, and then we stop, what would be the consequence? And what is the is there any data on the toxicology effect of curcumin?
As you know that people who come from South Asia, they have been taking their whole life curcumin, which is primarily turmeric, and turmeric contains, depending upon which part of the country it is coming from, as much as 8% curcumin. So there is no problem at all. FDA have done their own studies, toxicology studies, and they published 300-page report. And as far FDA goes, curcumin is a grass, which means generally regarded as safe. So they have no concern. And there is a clinical trial that came out of University of Michigan, where they did the human trials, and they went as high as 20 grams per day for even up to 3 months. They could not reach a toxic dose. So I'm not saying that anybody should take that kind of doses. So I think it is not necessary. Just to give you an idea that to down-modulate all the pro-inflammatory biomarker, that what I just told you about, that there is a clinical trials in human that as little as 150 milligram twice a day is sufficient. And mind you, that is 1/3 the size of aspirin, and that amount is sufficient to down-modulate TNF, IL-1, IL-6, endothelin-1, and malondialdehyde. And this is human trial.
I have a question. I know because I have a paper on curcumin that it has a number of functions and inhibits several transcription factors. Which one do you think, there has to be an upstream, do you think there is an upstream major mechanism that justify all these actions of curcumin?
I think it does not have to be, in my mind. It is just a matter of where you are focusing. So there does not have to be a single mechanism. And initially we thought that the NF-kappa B was the primary mechanism, but I will be the first one to admit that's not the only mechanism, because after all we are talking about here a chemical molecule that has a certain groups that interact with various proteins. And curcumin is known to interact with the cysteine groups in lot of proteins, if you look through. So depending upon where the cysteine is located in the protein, curcumin will interact. So does not matter whether that cysteine is coming from NF-kappa B or somewhere else. So I think that there are a number of mechanisms and number of targets that curcumin has. And for example, glutathione, this GSK3 beta, curcumin binds as much as a picomolar affinity, whereas some of the others, it is a millimolar. So I don't think there is any primary target that I know of.
Okay. Yes,
Almost the same question. We try to study since a while the curcumin for some effect we can discuss later. And the emerging idea is that we need a common mechanism, otherwise it is too much. And from our point of view, well, part experimental work and basically on the screen of the literature, it makes a lot of sense, at least for us, the increase on nucleophilic tone by the activation of LF2 through KEAP1. There is specificity for reaction, the micro-addition, the release the KEAP1, then the control of inflammation, the control of mitogenesis. Makes long story short. What do you think about the common mechanism related to the increase of nucleophilic tone?
Well, if you want to think about the common mechanism, I would say it is inflammation.
Yeah.
I think that if you stick with the word inflammation, and then at the chemical level, it becomes primarily is NF-kappa B, as I already pointed out. So, however, if you modify the curcumin and the curcumin undergoes metabolism, as I mentioned, that it becomes tetrahydrocurcumin, if it is, which is a white curcumin. Now that has a different kind of profile as compared to the basic curcumin, that yellow what you see. For example, metformin, as you know that the way metformin works is through activation of AMPK, and curcumin was found to be 400 times more potent than metformin in activation of AMPK. But curcumin metabolite, which is tetrahydrocurcumin, is 100,000 times more potent than metformin in activating AMPK. So you can very well imagine, so depending upon the type of situation and the type of metabolite we are talking about, that it may have a different mechanisms as well.
Okay, thank you very much. And